Hi, I'm Fernando Pereira from UFMG, and today we shall demonstrate formally that interference graph of programs in SSA-form are chordal. Do you remember the key property of SSA-form programs? It had to do with dominance. It's easy to prove this property. Can you read the definitions in this figure? Go ahead and stop the video to read them over. Anyways, with these definitions, which I'm assuming you read in the figure, let's prove this theorem. Actually, try to think about it. I'm giving you a hint on the right of the figure. If there is a variable whose definition does not dominate all its uses, then there is a path from the beginning of the program to this use that does not go across that definition. In this case, the program cannot be strict, what contradicts one of our premises. Here's another interesting fact about SSA-form programs. If any two variables interfere, then there exists one of them whose definition point dominates the definition point of the other. Would you like to try to prove this theorem? We may use this figure on the right. You can stop the video and think about it. There's a short proof here, which I advise you to read. Basically, if two variables interfere, then there exists a program point in which both are alive. That's the definition of interference. We call this program point L. The rest of the proof follows by a reduction to absurdity. Just imagine that neither definition point dominates the other. It's easy to find a path to L without going over the definition point of these variables. And then the program would not be strict, like we did in the first theorem. We have another lemma of similar proof. Consider a strict program, and let u and v be two variables that interfere. Let's assume that the definition point of u dominates the definition point of v. Then u must be alive at the definition point of v. Would you like to prove this lemma? There is a figure on the right side of the slide to help you out. The proof is relatively simple. We just need to show that all these paths in the figure exist in the CFG of the program. We know that there is a common point, call it L, where both variables are alive. We know that there must be a path from du to dv, where du is the definition point of variable u, and dv similarly is the definition point of variable v, as that comes from the definition of dominance. Anyways, we know that there must be a path from dv to L, from Theorem 1, which we had already seen. And finally, we know that there must be a path from L to some use of u. This also comes from Theorem 1. Let's now move on to lemma 3. This lemma talks about the relation between any three variables, call them u, v, and w, so that u and v interfere. V and w interfere, and u and w do not interfere. In this case, if the definition point of u dominates the definition point of v, then the definition point of v must dominate the definition point of w. You can try to prove the lemma. You will need to use the two previous lemmas. I'm giving them to you on the bottom of the figure. And I know I'm giving you a lot of lemmas. You may decide to stop the video and read them over again so that you make sure that you are on track. From lemma 1, either the definition of v dominates the definition of w, or vice versa. Let's assume that dw dominates dv. We know from lemma 2 that w must be alive at the definition point of v. Lemma 2 also gives us that u must be alive at dv, because du dominates dv. However, that's absurd, because the premise of the lemma says that u and w do not interfere. Therefore, dv must dominate dw. Now that we have lemma 3, we can prove the main theorem of this class on SSA-based register allocation. The interference graph of an SSA-form program is chordal. To see that the theorem is true, we shall use this figure on the right. So, we must prove that the interference graph of an SSA-form program has no induced cycle with more than 3 nodes. To see that such is the case, let's look into chains of interferences that are chordless. In other words, chains of nodes so that any 2 consecutive nodes interfere, but non-consecutive nodes do not. We sort the chain by dominance. So the first vertex, say x1, dominates x2. From lemma 3, that forces x1 to dominate x3. And we can generalize that to show that xi dominates every node xj if j is greater than I. Now, let's assume that there exists interference between x1 and xn. If that's the case, then there must be a program point that's dominated by both variables, that is, x1 and xn. Let's call this program point L. L is dominated by dn, and every other node dominates dn. Therefore, L is dominated by every node. But then there must be a path from di to L for any I greater than 1 and less than n, because di dominates L. This path cannot contain d1 because di does not dominate d1. But there must be a path from d1 to di because d1 dominates di. In this case, x1 must be alive at di, and that contradicts our initial assumption that says that non-consecutive nodes do not interfere. Well, I know that was a lot of lemmas and theorems. I know it's impossible to understand them by just listening to this video, so I recommend you to go back to the slides and take a look into the lemmas just to make sure that you understand what's going on. And with this proof, we conclude our demonstration that SSA-form programs have chordal interference graphs. In the next class, we shall see how we can color chordal graphs in polynomial time.